physics students. This is going to probably be the last live learning thing that we do this year. So we're going to try and go out on a bang here. We've got one more PhET lab for you. We're going to be doing the circuit challenge. So you're going to be using the same simulation that you did for the lab last week. Except in this one, it's going to be a lot of it's going to be, you're going to be doing the math on your own and then using the simulation to check and see how well you did on your math. So of course, there's nothing really stopping me from, or stopping you from cheating and doing it in the sim first and then just using that to get all your numbers. But it's a good idea to make sure you know how this all works. And so I'm going to model a couple of these for you and point you in the right direction. And then, of course, if you have any questions while you're working on this, feel free to get in touch with me. So first of all, we go back to the same sim that we were on last time. Oh, somebody is ringing my doorbell, but I don't see anybody else showing up here. So we're going to go into the same tab. We're going to click Lab. Now this is really similar to if you just played around in the Intro tab. It's using a lot of the same tools. One thing that's different is we've got this tool right here. This is an inline ammeter. So it's going to read the current, but instead of just having this thing here where you move your probe to a certain part of a circuit, this one much more like an ammeter would in real life. You actually incorporate it into your circuit and it measures the current that's flowing through it. So let's take a look at the instructions on our lab here, if it'll let me. Okay. So the first thing it wants me to do is it wants me to fill in the table for this circuit and then work it by hand and then build and check my answers in PhET. So you see in this circuit right here, we've got 3 resistors laid out in series. Now the thing to keep in mind for series is that in series, current is constant, SIC. So whatever our current is, it's going to be the same current all throughout the circuit. So we've got 3 resistors, resistor 1, 2, and 3, with these 3 different resistance ratings, 78 ohms, 15 ohms, 33 ohms. In series, your total resistance is just the sum of all of your resistors, so it's going to be very easy for us to find total. We just add up our 3 resistances, so that's 78 plus 15 plus 33. I get a total resistance of 126 ohms. And so if our voltage, our total voltage is 14 volts, because that's what's coming from our cell right here, then we can figure out what our current is going to be using our magic triangle, V over I and R. So if I'm trying to find I, it's going to be voltage divided by resistance. So I'm going 14 divided by 126, which gives me a current of 0.11 repeating. I'm not sure what that would be as a fraction, and I don't care, because I'm going to be perfectly happy going with 0.111 amps. And that should work fine for us. Okay, so that's 14 volts, 0.111 amps. Since in a series circuit current is constant, then the entire line right here, we can go ahead and fill in, is going to be 0.111. And then when we go to calculate our voltages, voltage for any one of these resistors is going to be current times resistance. So you're going to just be taking 0.111 times 78, 0.111 times 15, and 0.111 times 33. when you do that, those three should add up to 14, and that's going to be a really good indicator that we got it right. I'm just going to work one of those right now. I'm just going to do this first one. It's going to be 0.111 times 78. So I'm going to just take my answer times 78, and I get 8.66 repeating, so we can call that 8.67 volts. Now, it does say after I fill this in to build this in the sim and to check and see how accurate we are. So I'm going to do that next. We're going to drag out a battery. I'm going to click it. We're going to make it 14 volts. Let me go ahead and show values. That's going to make things a lot easier. I'm going to move this out of the way for right now. So I need 3 resistors, U, and U, and U, and let's see. So resistor 1 is 78 ohms. So I click on this, make my value 78. R2 is 15. And then R3 is 33. Going to connect all these with wires. Doesn't have to look exactly like it does in the drawing. Drawing is just a schematic for us. And boom. Okay. So we have current. It's a really, really slow current. We can check a couple of things. Let's check our current here. And according to our current, we have 0.11 amps, which is exactly what we had predicted. We want to look at what the voltage is on either side of resistor 1. So let me put this up. Let's get out our voltmeter. So I'm going to put one of my probes at this end. I'm going to put the other probe at this end. And it says I have 8.67 volts. And 67 volts is exactly what we had predicted. So the simulation supports our calculations, and that's always a good thing. Let's look at part 2 here. Part 2, we've got a parallel circuit. It's got 3 resistors, each on different paths, connected to a 120 volt battery. And it gives us the 3 resistors. So they want us to build the circuit in the simulation and paste a screenshot into the table. So we have what, 5, 7.5, and 9.8. Okay, we can do that. So let's break a few connections here. Just going to, you could just hit reset and start over. I'm going to choose not to then. So let's see, 5 ohms. Except I think I just spotted a problem with the lab. No, 5, 7.5, and 9.8. Actually, yeah, I do have a problem because you can't get 0.8. And let me check another thing. Let me make sure we can do 120 volts, because if we can't, oh good, we can do 120. That's as big as it gets. So this needs to be 7.5. Now on this last one, since we can't do 9.8 ohms, I'm just going to make this as close as I can get, so it's just going to be 10 ohms. Well, I think 9.8 is slightly closer to 10. What we can do is we can do calculations according to what it would be if it was 9.8, and we can actually see how close that is to 10, or we can just do it and call it 10 and make some adjustments on our table. It's going to be close enough either way. I'm really fine whichever of those two you choose to do. But what I'm going to do is I'm going to set up Junction right here. Wow, look at them go. Set this up coming across here. Oh dear, I have set things on fire. That's a problem. So let me break this for just a minute. All right, so this is not going to be a safe circuit. I may be about to make a judgment call on this particular chunk of things. Oh, you know what? I think maybe that should have been 12.0 volt. That would, let me change that and see if that actually makes this less, explosive here. I like that a lot better. So let's go ahead and say that that was a typo, and I'll get word out to everybody that instead of 120 volts, this is supposed to be a 12.0 volt, or just a 12 volt. And instead of 9.8 ohms, we're going to make this one here 10 ohms. So then the total would not be 22.3. Actually, it would not be 22.5 either. So here's our circuit. Here's the one that I'm going to choose to use. I'm going to take a screenshot of this. So let me get my handy dandy screenshot tool. Get a new snip here. Let's go. Yours, of course, doesn't have to look just like this. It can look a lot prettier. Or not. Okay, so let me copy this and paste it into my I'm not sure I've actually got I do have that open. I've got it open right here. I'm going to come down here where it says insert screenshot here. I'm going to paste it in there. See how badly it breaks things. That's not terrible. I'm feeling pick a little bit smaller. Still want it to be legible. That's probably okay. I can make things out on that. Okay, so I've built it. Paste it into my list on my table. Need to complete the table. So let me come back out to my paper copy. Now, since this is a parallel circuit, remember the rule of thumb for parallel, we think PVC. So in a parallel circuit, voltage is constant. So if our total voltage is 12 volts, that means that it is going to be 12 volts for every part of our sim. Now remember, when we're totaling up resistance, we're not just going to do a straight across the board addition, because resistance, let me find scratch paper here. Resistance in parallel, you do 1 over resistance total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So in order to find our total resistance, we have to plug stuff in here. So that's going to equal 1/5 plus 1 over 7.5 plus 1 over 10. And then that's going to equal 1 over our total. So I'm going to solve first of all for these, and then I will flip it over in my calculator. So get it where you can see it. So 1 divided by 5 plus 1 divided by 7.5 plus 1 divided by 10 is a number, and then I go 1 divided by that answer to invert it. And it looks like I've got a total equivalent resistance of 2.3076. So I'm going to just call that 2.31 ohms. And that was something, if you were paying attention to that last resistance thing on the word problems that we did yesterday, when you're looking at total equivalent resistance for a parallel circuit, it's always less than any of the single resistors that are in there, and that's certainly less than the smallest one we had. So that seems to make sense. Now, what we're going to do is we're going to calculate current for each of these. So we can define current, that's voltage divided by resistance. So if we go 12 divided by 5, let's see what that gives us. That gives us 2.4. Okay. Let's see. I'm going to just do a quick survey in my head. So let's see if we do 2.4, 1.6. I know you can't see my writing. Okay. And if we do 12 divided by 10, that's 1.2. Now, these are the three that I got. If I was just going to total those up, then 2.6, that's 3, 4, then I would get 5.2 amps from my total. Now, if I go straight this way and I go 12 divided by 2.31, I get 5.19. Check that out, which is awfully close to this 5.2. So the math is all going to work out there. Anyhow, I'm not going to finish filling in this table for you. I'm going to let you do that, but I do want to do a couple spot checks in my circuit to see how closely this matches up with what I would expect to see. So we're looking to have 12 volts at resistor 1, and we're looking to have 2.4 amps of current. So here's resistor 1. Let's get out our voltmeter. If we measure across that resistor, sure enough, that is 12 volts. And if we want to look at current going through there, we calculated 2.4 amps, and so let's take a look here. And that's showing a current of 2.4 amps on the dot. So again, that fits what we would expect to have seen. Let's come down and look at that's not the last part. Part 3 is a complex circuit. So it wants us to determine the voltage on and the current through each resistor, and it wants us to do the math on our own and then build it and check it in the simulation. So now, because this is a complex circuit, we can't just rule of thumb and say that PVC is sick. We're going to have to actually do a little bit of thinking this one through. So if I see in this sim right here, or in this circuit right here, these two are connected in parallel to each other, but they all together are connected in series with this one here. So when we go to calculate up our total resistance, we've got the 6 ohm resistor and the 9 ohm resistor in parallel. So total resistance for just this portion right here, 1 over R, is going to equal 1 over 6 plus 1 over 9. So calculating that, 1 divided by 6 plus 1 divided by 9. I get that. and I want to invert it, so I do 1 divided by answer. So I get a total resistance for just that portion of 3.6 ohms. I'm going to make a note of that for myself. Now, if that portion right there is 3.6 ohms, and it is in series with the rest, excuse me, in series with the rest of this, what that tells me is I'm going to have a total equivalent resistance of 6.6 ohms. Okay, again, because that and that are in series with each other, so I can at this point apply my rules for adding series resistance. I'm working with 12-volt batteries, so it's going to be 12 total volts. I can figure out my total current from here by doing volts divided by resistance. So if I do 12 divided by 6.6, then all of my currents, if I end up calculating this right, should be 1.818181 repeating. So I'm just going to call that 1.82 amps. So this gets a little bit more complicated. I think at this point I'm going to do a little bit of cheating myself. I'm going to build this circuit in my construction kit. So let me, just going to come down here and reset. Let's see what parts I need for this. Okay, I need a 12-volt battery. I'm going to need 3 resistors with 3 ohm, 6 ohm, and 9 ohm. Okay, let's try and put them more or less like they are in the picture. Show my values. So this guy over here is 3 ohm. This guy right here is 6 ohm. And this one down here is 9 ohm. Okay. These two are wired in parallel to each other, so I'm going to have wires coming out like that. And they're going to be in connection with this guy here. Battery up here. And then this right here. So that is a working circuit. Now we can tell just by looking at this that we're getting different currents in different places in the circuit, because the places where the electrons are moving fast, that's high current. Okay? If I just drag my contactless ammeter around here, I can see that on this side I've got a current of 1.82. On this side I've got a current of 1.8, but it differs at different places around my circuit. Now the 1.82 is important because that's what we had calculated as being our current on our table over here. So that checks out. Now, making a few observations right here, it looks like the current is going at 1.82 everywhere in this circuit except in these two little branching resistors down here, except in the parallel part. So I think for our 3 ohm resistor, it's a safe assumption to make that the current right there, since we're considering that to be part of a series circuit, that for at least that chunk from here around to here, that current is going to be constant. So I'm going to predict that current on my 3 ohm resistor is also going to be 1.82 amps. And I can check that real quick. Sure enough, that is 1.82. The math might be a little more complicated right here. So if we've got so let's say that we've got a total current of 1.82 coming in on this side and going out on that side. So what we've got to do to figure out if total current right here is 1.82 for these two things right here, then what we can do is we can figure, okay, what portion of that is being shunted through this one and what portion is being shunted through this one, because I think there's going to be proportionality to it. Now we said that our total resistance down here was 3.6, right? Okay, so if for this portion of our circuit, if PVC is true for this part, then that means that we can get a total voltage. So our total voltage here, if we've got a total resistance down here of 3.6, and if the total current coming in across that thing is going to be 1.82, then I think what we can do for each of these is, well, no. Okay. Total resistance. Okay, so maybe, I'm not sure what direction we want to take this in. What happens if we just try and what if we assume that the voltage here is 12? I'm going to see if that's a safe assumption to make. I'm going to cheat and I'm going to pull out my voltmeter. I'm going to see if the voltage across either of these batteries happens to be 12 volts. It is not. Voltage right there is 6.55. Is it 6.55 across this one too? Now that at least is good, okay? So I don't want to pretend like I cheated. I want to figure out, okay, so how could I figure that out if that was not already a thing? I know how I could do it. I think I've got it figured out. Okay, so look here at our table. If we know just for this resistor right here, we know the resistance and we know the current, we can find the voltage. Voltage is equal to current times resistance. So let's do 1.82 times 3. Let's turn the calculator on before we start punching in numbers. It works better that way. 1.82 times 3. I get 5.46 volts right there. So let's look. 5.46, which means that for this portion of our circuit, we've got 5.46 volts going, or 5.46 volts going through just that guy right there, which means that the rest of this has to total up to 12. So what if we do 12 minus 5.46? Let's do that. 12 minus our answer. I get 6.54. Look on our sim. Okay, that's sick. That is sick. All right. So that's how we would have figured that out. I would have figured 6.54, according to my calculations. Okay, now we can figure out mathematically what the current would be for both of these. If the current is volts divided by ohms, voltage divided by resistance, we do 6.54 divided by 6, I get 1.09. And if we do 6.54 divided by 9, I get 0.726 and change. So let's call that 0.73. I'm going to cheat now, and I'm going to use my current meter going through both of those. So according to my calculations, Going through the 6 ohm resistor, I should get 1.09 amps. 1.09. And going through my 9 ohm resistor, it should only be 0.73. It should be slower. And it is 0.73. Hot dog! I love it when things work out. Even if I'm not entirely sure why they do, it just makes me feel a little bit better about the universe that something makes sense. So now that takes us to, find my camera there, okay. That takes us to the second page. Now, on this second page, we need to construct a complex circuit that will produce a specific amount of resistance. And we have to use these components right here. I am going to do a quick check on something here. I'm going to pull out a sample resistance, and the sample resistance I'm going to pull out, just for absolutely no reason at all, is going to be, let's do 76.92 ohms, just for the heck of it. Let's see, 76.92 ohms. Okay. Now on this one, we full well are going to be playing around with things. We need a 100 volt battery, 120 ohm resistor, 100 ohm resistor, 50 ohm resistor, and 40 ohm resistor. So I'm going to reset my circuit and get all those things ready. We need battery, 4 resistors. I'm going to turn on values so I can see what everything is. Battery is 100 volts. I've put a little picture down at the bottom of that second page of all the parts that you're going to need to use. So 100 volts. I'm going to go ahead and attach this inline ammeter to this because it's going to measure my total current for my circuit even while I'm changing things around. So we have 40, 50, 100, and 120 for my resistors. And 120, as big as I can get. So we are supposed to connect these in such a way to where they give a total target resistance, in this case, of 76.92. So I'm just got some wires. Some of these, what happens if I put them all parallel to each other? That's going to be my first test. Wire down here, wire coming down here. And I'm just going to connect each of these to this point here. Make sure I've got that actually hooked up. There we go. And each of these to this one over here. Now that gets me 6.33 amps, and so that's, now, all right, it tells me amps. What that does not tell me is total resistance. And so what we can do, let me break that real quick. If we are trying to get, let's say, 76.92 ohms using a 100 volt battery, then what would be the total current on that circuit? Well, I equals V over R, so if I do 100 divided by 76.92, let's see what that is. Okay. So you are shooting for a target of about 1.30 amps. And you'll know that you've got the right resistance load if that is the number that shows up on your ammeter, 1.3. And you can see connecting that, that's definitely not 1.3. That's fast. So we need to figure out some way to configure these to slow these electrons down even more. So what if, let's break this, what if we try and take some of these bigger ones, and instead of having them in parallel to each other, what if we try and put them in series to each other and then hook it back up? Okay, we're getting closer. That's definitely lower current. It's still not down to 1.3. So maybe I will add a third one of these in series, or maybe instead of having the 40 and the 50 in series, what if instead of that I have, oh, you stop it. What if I have the 40 and the 100 in series to each other? So let's drag you up here. Let's reconnect you in parallel. 3.5, nope, that doesn't quite do it. But do you see where I'm going with that? You're just going to play around with which of these are in series, which of these are in parallel, until you get that target current. In your case, it's 1.3. In someone else's case, it will be different depending on what number I gave them. And then once you've got it built, you're going to just take a screenshot or make a sketch that you have that works, and you'll be done. That's probably going to take the bulk of your time, is just playing with that very last one. But I guarantee you, the numbers I gave everybody, I didn't just pull out of a hat. They are ones that you can make using this, because I've made them. So that brings us to the end of the video on this. This one ran pretty long. I'll maybe see if I can trim it down a little bit. But as always, if you have any questions or any comments, feel free to get a hold of me. And good luck.